Ladies and gentlemen, please welcome Ashley Kowalski of the Aerospace Corporation to the stage.
I got you, moonlight, you're my starlight. I need you all night. Come on, dance with me. I'm levitating. You, moonlight, you're my starlight. I need you all night. Come on, dance with me. I'm levitating. I'm one of the greatest.
Everybody sits in the back.
All right. Everyone hear me all right? Sounds good. All right, so good afternoon, everyone, and welcome to our panel discussing whether astronaut analogs are useful preparation for long-duration human spaceflight. My name is Ashley Kowalski. I am a project leader in the International Partnerships Department at the Aerospace Corporation. But in addition to that role, I have myself participated in two different astronaut analogs. The first being Sirius 21, which was an 8-month-long isolation mission held in Moscow, Russia. It was a collaboration between NASA Johnson's HRP program, Human Research Program, the UAE Mohammed bin Rashid Space Center, as well as the Russian Institute for Biomedical Problems. I also participated in the Mars Desert Research Station, the first all-aerospace analog mission just this past year as well. Enough about me, though, because we have some amazing colleagues here on the panel with me. So first on my panel, I have Dr. Sandra Magnus. So she is the Chief Engineer for the Traffic Coordination Systems for Space at the Department of Commerce. In addition to other distinguished roles at the DoD and AIAA throughout her career, Sandy was also selected to be a NASA astronaut in 1996. She flew several shuttle missions, including the final shuttle flight in 2011, and has also spent around 4.5 months on board the ISS. Dr. Brandon Vessey, he is the element scientist for NASA's Research Operations and Integration Element at NASA Johnson Space Center in Houston. In this role, he provides scientific oversight for spaceflight and ground-based analog studies conducted by the Human Research Program. And finally, we have Dr. Miroslav Rozložník. He's the Chief Scientific Officer of the Hydronaut Project, which is the European hybrid module for underwater research and training facility, and it's based in Prague, in the Czech Republic. He's a member of the International Guidelines and Standards for Space Analogs, and he is an environmental physiologist, aquanaut, analog astronaut, and also a hyperbaric medicine expert with 20+ years of experience. So we'll give a quick round of applause to our panel. And throughout this panel, you'll see we have a slideshow going on. So these are various images that we've submitted from HERA missions, from Sirius 21, from Mars Desert Research Station, and various other analog studies. So without further ado, I am going to start my panel session with a question to Brandon. So not everyone here in the audience might know exactly what an astronaut analog study is. So I'm hoping that you can first start us off by explaining to the audience, what is an analog mission? What is the intent behind the missions? What are the types of analogs that NASA is involved with? And what does NASA hope to learn from these analog missions?
So I will try to take that one at a time. I may need some
It was
reminders.
a mouthful, sorry.
So at least from the standpoint of the NASA Human Research Program's analog missions are really any kind of mission where we're able to simulate some of the effects of spaceflight on the human body, the human mind, without actually necessarily needing to go to spaceflight, or at least not the specific mission that we're trying to simulate the effects of. For the Human Research Program, we're really focused on kind of 5 major risk areas: radiation, isolation and confinement, distance from Earth, gravitational effects, and extreme environments. So anywhere that we're able to simulate some of those effects from those different areas, we consider an analog for spaceflight. For us, those missions the purpose of those missions is really, we can't do everything in spaceflight. The ISS has a limited shelf life, and even within the time we have available on the ISS, we only have so much crew time available. Crew time is one of our most precious resources, so we have to use it really wisely. Anywhere that we can get similar or pretty close to what we would be able to get out of an ISS research study on the ground without using those resources, it's really to benefit for us. We're able to, using these analogs, turn the research around a little bit quicker with less expense. Going to space is really expensive. So it meets multiple needs for the human research program, and you'll have to remind me on the last couple of points you wanted me to touch on.
Specifically, if you can name some of the specific analogs that NASA's currently doing, and what are some of the specific research objectives that you hope to learn from them?
Yeah, so really the main categories of analogs that we've been working with, isolated, confined, and controlled environments. So think of these like your habitats that aren't, they could be in the middle of Moscow, like in the case of Sirius 21, in the middle of Houston, like in the case of Hera. But there's an aspect of control to those while you're still isolating and confining the people inside of the habitat. Isolated, confined, and extreme missions, these are more like field studies. You could think of Arctic, Antarctic, underwater missions, where you've still got that isolation and confinement component, but you're adding in the effect of the extreme environment on top of that. Parabolic flight, really good for looking at least short-term effects of microgravity or different variable levels of gravity, which is something we've been doing lately. Bed rest studies, again, primarily looking at the physiological effects of unloading the body, so again, kind of those microgravity effects. And also radiation, although I'll caveat that with not for human studies, but for studies where we're using different models to learn about the possible effects on the human. Those are the kind of general categories, and then within each of those categories, we have multiple venues that we do research in. As far as types of research we're doing, it really runs the gamut. I mean, you can, for at least the work the Human Research Program does, pretty much all of it can be done to some degree in the analogs. Psychological and behavioral studies, physiological studies, looking at things like SANS, cardiovascular effects, immune effects, technology development and testing, medical procedures. It just really runs the gamut for us.
Thanks. So, next question is for Sandy. So, astronaut analogs, they have been conducted for decades. I was even able to see in person one of the first Soviet ones that was built back in the 1960s. And I remember it being like a small 10 by 10 by 10 box, basically. So now we have a lot of different analogs, as Brandon was just saying. We have analogs in the desert, we have them in Antarctica, we have them underwater, we have new facilities sprouting up all the time, the new Houston Chapea facility, all of that. So some are habitat focused, some, like Brandon said, are psychological and physiological. But you commanded the Nemo 11 mission back in 2006. That was an undersea simulation. So what I wanted you to expand on is, how did you feel in that simulation? What was the experience like? And what most stuck with you during that simulation?
Yeah, so before I answer your question, public service announcement. I'm representing myself on this panel, not my employer, MITRE, or the place where I am working full-time, the Office of Space Commerce. So I had to get that out there. So to your point, Nemo 11, so I had 3 unflown people with me, and I, of course, had flown already on 1 shuttle flight at that point. And Nemo, just for those of you who are not familiar with those missions, it was NASA using the Aquarius habitat off of Key Largo to do some investigations of a couple of things, what it would be like to put people in a remote environment and then have some interaction with, a remote mission control with respect. There was a little rover that followed us around on the bottom of the ocean, which was kind of fun. What does that dynamic look like? How would we plan our days in a more remote kind of a scenario? We were doing some testing of some surface suits with respect to CG and things like this. So there were specific exploration objectives. To me, it felt very much like a shuttle mission in that there was a daily schedule. of tasks that they wanted to do. There was communication going back and forth with the ground control, if you will, the mission control. When we had questions, they had cameras where they were watching us. It's very much like being in space. So from that sense, it was good training. Now, what we were trying to sort out is strategic versus tactical, and who controlled those different pieces. For the crew that was with me that hadn't flown before, they hadn't had an opportunity to work in mission control as well. When you work in mission control, you kind of see the view of the world from the other side of the team, from the different viewpoint. You learn a little bit more as a crew member how to engage with mission control when you've actually lived in their shoes as a member of that team. So it gave them a feeling for how to, what kind of information to communicate, how to communicate it, how to be clear, anticipating a little bit of the kind of needs that they had. And so it was good for that purpose. And those kind of dynamics will change the further and further we get out from the surface. What we need in low Earth orbit versus how we want to set those dynamics up, and those different roles and responsibilities going to the lunar environment and then onto Mars are going to be different. So the analogs should continue to explore that differentiation.
Now, you mentioned some similarities, obviously, between things like the schedule and some of the operational aspects of mission control, but you were the only one, again, on that NEMO mission who had been to space previously. Mm-hmm. So when you went back to space after that NEMO mission, did that give you a different perspective or an edge, or do you feel like it didn't really help too much? It was pretty much...
No.
Exactly.
Because the other thing, there's a big difference between flying a shuttle mission and flying a space station mission. It's a completely different pace. The kind of training you do is different. Your engagement with mission control is completely different. On the shuttle missions, we were very time constrained. I mean, our schedules were planned out, no kidding, to the 15-minute interval. And we had backup plans, and, because we had things to do, and we had a finite amount of time to do it. And so the Capcom role in the shuttle control room was an astronaut who you could sort of do that translation function between what the ground wants and how they need to ask it, and understanding how the astronauts are going to receive the information in the most effective and efficient way. So it was all about efficiency, efficiency, efficiency. When you fly on space station, it's like, you're going to be there next week. You're going to be there next month. So there's time to work through problems. And we got to the point in the space station control room where the Capcoms aren't astronauts. And it became we realized after several years, like, what, if I need to talk to an engineer about a piece of equipment that I'm doing a repair on, I'm just going to talk to the engineer, which is very not shuttle, very not the way the shuttle control room. So it's a different dynamic based on the length of the mission, how we're trained as generalists on the space station. So we have a little bit more autonomy as far as the types of tasks that we're doing, because we have to do all those tasks. On shuttle, you get trained on, you're going to be the person that does the photography and manages that, or you're going to be the person that does logistics, or you're going to be the person that sets up the computer network in the shuttle right when we get to orbit. On station, we had to be able to do all that stuff. So it was a completely different paradigm.
Okay. So I'll give you a break for a little bit and go down to Miroslav. So, Miroslav, you are the Chief Scientific Officer for the Hydronaut Deep Lab facility. So once again, that's a research and training station designed for short and long-term stays for small crews. And that can be done both underwater and on the surface, which makes it a unique hybrid facility, right? So can you tell us a little bit more about how your facility is unique compared to other analogs that are out there today? And can you tell us a little bit about the research goals that you hope to achieve?
Yeah, so our habitat, as you said, is unique in different aspects. So first of all, we are hybrid, so we can be operational both underwater and on surface. And actually, we just finished our 5 years underwater and now moved to Prague, where we will spend some years on surface and move underwater again. We are also mobile, so we can transfer from one place to another. I mean, the habitat weighs 35 tons. It's, manageable. So that's unique. And the last thing I would say is our size, because the crew module inner volume is something like 20 cubic meters, which is roughly like 700 square feet, if I'm not wrong. And the living area is about 8 square meters, so roughly 20 square feet, something like that. So it's very confined environment. And this is also our advantage because we also want to focus more on transportation. I think there are a lot of analogs which focus on operations like being on lunar surface or Mars surface, but transportation is not addressed. So, I mean, our side probably address this need, and we can be utilized for simulation of different transportation scenarios.
So, Brandon, we're looking to, of course, send humans back to the moon and onto Mars, hopefully, and who knows where from there. So we have some real technical problems that we need to tackle, some risks that we need to mitigate. So what are some very specific mission-critical risks that NASA Johnson is working on today, and how are the simulations helping to answer those challenges?
Yeah, so again, for HRP, it really covers our whole sort of risk portfolio. That's how we kind of categorize the research that we do, is looking at what risks for human exploration we can mitigate, understand better, be able to measure better, that sort of thing. Some of the examples of the more serious risks, we call them red risks, that we look at in the analogs, specifically team functioning and performance, especially lately looking at multi-team functioning, so how the team dynamics are going to develop and how the teams are going to perform when you're looking at the crew on the mission and mission control when you're in a much more autonomous communication delayed environment. Looking at that both across shorter time delays, more on the order of what we expect for lunar missions, as well as much longer time delays that we're looking at for Mars. But not just from that aspect. We've also seen in many of the analogs duration component of the team functioning, where there seems to be I'm not going to call it a sweet spot, maybe a bitter spot around the 6 to 8 month mark, where friction seems to more easily develop in the teams, and kind of at any point beyond that, things that might have been smaller disagreements become larger disagreements. And so better understanding the dynamics of that and how to mitigate that in future missions. Providing behavioral health support in an autonomous fashion. You know, most of our mitigations relative to behavioral health support right now are reliant on real-time or near real-time communication. We're not going to have that when we go to Mars, so how do we provide that level of care? One of the more interesting things we've been studying, and more critical things we've been studying lately, because it's not just a future like lunar or Mars mission risk, but it's current risk on ISS, is SANS, spaceflight associated neuroocular syndrome. So this is where we've seen actual changes in the eye in astronauts that are flying on ISS for a long period of time, and some associated symptoms with that. We've been studying that in bed rest facilities, and actually as of a few years ago, we're able to successfully introduce those symptoms into bed rest participants where it hadn't been seen before, through a very rigid program of keeping them at a 6-degree head down tilt, no kidding, all the time, when they're eating, when they're sleeping, no flexibility around that. We were able to see a very similar pattern of symptoms to what we see on ISS, and so now we're testing countermeasures in those same bed rest facilities to see, okay, we've seen the symptoms occur in this analog, what can we do in this analog to prevent or kind of walk those symptoms back, and then take what works best there and implement it in spaceflight to hopefully mitigate what's happening with the astronauts on ISS. So those are a few examples. Like I said, though, it really does run the gamut for HRP.
That's really interesting, because that you mentioned like the 6 to 8 month mark of a mission where things turn. Sometimes maybe there's a little bit of it's not altercation, but maybe some breaking points between mission control maybe and the crew, or because I know when we did our 8 month mission, I do feel like I remember around that point, that's when things started to have a little bit of a disconnect between the crew and the mission control, or maybe we just decided that no, we don't want to listen to them anymore right now. We just need a break, it's interesting that that is a pattern that is seen. But I'm also curious now, when you notice these behavioral differences in a crew, you can pinpoint, of course, using the data where in this mission that happens and perhaps why it happened. But how do you go about the risk mitigation part of it for the next crew? And like, how do you go about that by picking a different crew personality type the next time? Do you go through different types of training techniques prior? How do you go about changing that part?
Honestly, the first question is, do we want to change that? So is it something we actually want to interfere with? For us, a lot of times that comes down to what do we expect for the future mission? So you mentioned like picking a different crew. Are we going to expect to have that much control over team composition for a future mission where we can pinpoint where those issues are coming from with a potential crew and select somebody else if they don't fit together right? In many cases, there may be other drivers for that, political drivers, technical and skilled drivers that would override that sort of thing. So oftentimes, we may not actively mitigate for those unless they're causing actual problems that endanger the individuals in the mission itself, the science, but those are extremely rare. It's typically your lower level types of issues that can occur that, they're not desirable for the crew, but they're not going to hurt anything. They're not going to hurt anybody. They're interesting data on how things might develop in the absence of those mitigations. And they also give us an opportunity to try to see if we can predict some of those things happening on future missions. So that's one thing where if we assume, and some of our studies do this, they assume we're not going to be able to sort of perfectly select the crew at the beginning, but if you at least know what the crew looks like at the beginning, can you predict some of those fracture points? Can you say, well, these two people might have very differing personalities, and if you're putting them together on, in a rover on the lunar surface for a week, that may be a point where some tension could develop. So what do you do about that? And are you able to successfully predict that? So we're doing some of those types of studies as well, reflecting back on when we have seen those issues within the crews.
Very cool. And perhaps this is my ignorance here, but for actual crew selections, when the crew is actually selected and assigned to a mission, is that part of the planning process where you say like, well, these two personalities might work better or work not so well on a specific project, and they're assigned that way? Is that something that is actually seen in real life?
Are you asking about analog crew selection or astronaut crew selection?
I'll say, since you mentioned that's a thing for analog missions, I wanted to see, is it something that is transferable to actual crew missions?
So for the analog missions, we have some consideration of that, just from the standpoint of we want to select crews that will be able to complete the mission. We don't want to put anybody in there that, it's obvious they're immediately going to butt heads and not be compatible from the start and not be able to finish the mission, right? But beyond that, we try not to overly influence. That way we've got a good amount of variability in the data that we're getting back. Otherwise, if we're just, kind of picking a quote unquote perfect profile, you're really limiting the data set that you're looking at. For actual astronaut crew selection, I'll have to defer to Sandy for any insights on that.
I'm not sure. Do you have any insights on that?
No.
There
no,
you go.
no, I mean, no, I don't have insights. No, that's not a factor in crew selection.
Okay.
Crews are selected for the skill sets that are needed to execute the mission. And the crew is focused on executing the mission. And the crew figures out how to deal with any interpersonal relationships or team dynamics that need to get smoothed out in the execution of the mission. So, yeah.
So this is a general question for everyone, but I think I'll focus first on Miroslav. So this is an international panel, and as we prepare humans for long-duration human spaceflight, it is going to be more and more of an international challenge. My own Sirius 21 crew was, for the analog mission, was international as well. We had started out with 3 Russians, 2 Americans, and 1 Emirati crewmate. Miroslav, your facility's in Prague. You've collaborated with ESA and other nations. Sandy, you've worked with international crew on your missions. Brandon, NASA's done analogs abroad and at home. So, and I believe even UAE might be participating in a future HERA. So, Miroslav, we'll start with you. So why is all of this international collaboration so important, and how can the international aspect of aspects really contribute to the future of human spaceflight goals?
Yeah, so for us, I would maybe also differ it because it's not only about the astronaut, but it's also about the research, because you need to communicate also with researchers from different nations, and also it brings complexity. So for us, being underwater, we did some missions where we had international collaborations, like with Israel, for example. Now being on surface, we already established collaboration with Italy and with Taiwan, and we also had international crews. So we are starting to gain these experiences. So I would say my understanding is it's very vital, and we already see the differences. I think one of the benefits, and which probably needs some more attention, is about communication. Of course, our protocols are probably not so standardized as yours in NASA and during real space activities, but still we need to communicate with the crew as a mission control, with researchers, etc. And what we see from European perspective, we also need maybe to establish some special communication protocols just to be sure that everybody understands everything. Because this might be an issue for future. What we also see is that it really brings new dynamics to the team. We had a mission just with a Czech or Czech-Slovak participants, basically who speak the same language. We also had international ones. So yeah, it brings complexity to the missions. And I think it's extremely important to be conducted in analog space missions in this design.
Yeah, if I can interject a comment, the communication piece is really important. You have to be, as a crew, you have to be able to communicate. And one of the things that was always variable on the space station crews was the equivalency of language, English and Russian language between the different crewmates. So, for example, when I flew on space station, Yuri and Mike and I had the ability to speak equally in English and Russian, and we used both languages. We'd be at lunch speaking one, and we'd switch to the other, or we'd intersperse words in both languages in the sentences. But we had a pretty good relationship because we could communicate. So if you have crew members who cannot communicate because of a language barrier, and then on top of that, miscommunicate because there's a cultural barrier. Although quite frankly, as you work with someone over time, the cultural barrier becomes not as great of a thing because you start to understand each other as people, because you can communicate with each other. So the communication and being able to communicate clearly and efficiently, and really communicate, is super important in a crew, regardless of where you're going and what you're doing.
And just to insert some of my own experience into everything that you guys are saying, I agree 100%. When we were doing Sirius 21, for example, the Americans, we did have a Russian language requirement. I'd say the majority of the communications we did within the mission were in Russian, English being the second most, but we also had an Emirati crewmate who primarily knew Arabic and English, and the other American that was in there with us, he was a former Arabic linguist, so it was almost like 3 languages in there that we were kind of playing around with. And then the multicultural aspects, of course, between Russian and American and Emirati cultures, there are of course differences. There's plenty of similarities, and we did have to navigate through a lot of those to kind of create this cohesive, smooth environment. But I think that's a natural part of any crew, and it's part of what I loved about our particular mission when we did Sirius 21. So now, to everybody and whoever wants to take this question on also, so what, in your opinion, so if anyone here in the audience wanted to augment what is already being done for analogs, or something that needs to still be researched that maybe NASA hasn't gone around to, or maybe the Hydronaut program can't get around to quite yet, or anything? What is a thing that hasn't been touched yet, or that maybe just doesn't have funding to be touched yet, for example, but should be researched, that maybe somebody in this audience could tackle in the next couple of years to augment what is happening?
From our standpoint, the duration component is really important. So having analogs that are running realistic durations for exploration missions, talking on the order of many months to possibly a year or more, is important in being able to really see some of these time course effects. There are limited opportunities for that right now out there. Actually, most of our opportunities for that are in field settings, like the Antarctic. But to be in an environment that's a little bit more controllable where we can look at some of those effects. Another aspect that we oftentimes don't really get to touch much in the analogs is actual consequence of the choices you're making in the missions, because these are controlled studies. They are overseen by ethics boards, IRBs. You can kind of only push the stress so far. And for many of the research studies, that control is a really valuable component, because you can compare from one mission to the next mission to the next mission, because you know exactly, day 65, this is what the schedule is going to be, here's what they're going to be doing at breakfast, lunch, dinner, that sort of thing. But you lose that psychological aspect of, if I don't do this rendezvous activity correctly, I may not have access to this set of supplies for the next week or two until we can do another pass. That's something that has been explored a little, but in very limited capacity. So building some more consequence into the missions, hopefully somebody can figure out ways to do that while still maintaining some of the predictability control, would be really valuable from just a mission fidelity standpoint, especially for some of the psychological performance types of studies, because that is a little bit of a missing area at the moment.
Mm-hmm. Okay. And I'll just do a quick plug that if anybody did want to submit any questions, feel free to, I think there's scan codes on the tables, I believe, that you can submit a question if you want. Sorry, I didn't mean to cut you off at the end there. I think you're done. Did anyone else want to add to that bit right there? Okay. So this panel itself, we have been asked in our panel submissions to frame the session as a question, basically. So ours is basically, if I can do just a rapid fire, are astronaut analogs useful prep for high-stakes human spaceflight? Honest answers. If you go down the line, who wants to take that first? I'll say, do it, a quick short answer, just rapid fire down.
It depends upon how the experiment is designed.
Yeah, I think that's a really fair answer. It's critical for us, but it's got to be the right analog run in the right way.
From my perspective, I would agree what you just said before, that it needs to be high fidelity, and I would also say it needs to be, it should allow to be comparable, or you need to make hybrid studies like we did. So when we had different missions around on surface and underwater, and then you can make a comparison between the data to see the aspect of some hazards, how they influence crew at the same conditions, but same condition inside the habitat, but another conditions outside the habitat.
Now, Miroslav, before, outside of the sessions, we had mentioned briefly about analog standardization as an option. Do you want to touch on a little bit about that and how you feel about the standardization of analogs and how that could help or maybe not help in the future?
Yeah, I think at least from our kind of point of view in the human research program, we have been working with the international community around some standards. So there are standards out there relative to bed rest analogs, the types of data that need to be collected, the types of conditions, just again, to that kind of comparability standpoint, because otherwise, with a lot of these analogs, you're looking at crews of 4, crews of 6. They end up being 1-offs, 2-offs, 3-offs, but very small sample sizes. So the more you're able to have some of that standardization in the data that's being collected, the way it's being collected between the analogs, you can start to build those data sets and have some more direct comparisons across environments. We've recently developed a set of standard measures for isolation analogs, which we're hoping, and many in the international community are already picking those up. That was an international effort as well. But you know, it's a balance, right? It's nice to have some of those standards, but it's good for the science to have variability as well. So you can see what's driving differences between analogs that you might be able to apply to future missions, because we do have, you know, different mission profiles. If we knew there was one mission we're really worried about, and that's the only mission we're worried about, we could standardize everything against that. But humans and human exploration missions aren't that easy and simple, so we've got to really account for a lot, and having that variability in the analogs helps as well, because there's not one mission and there's not one analog that can perfectly simulate every mission.
Mm-hmm. And Miroslav, if you don't mind adding to that, because I know you're part of the, it's the International Committee for Standards of Analogs. I think I'm saying that incorrectly, but
Yeah, actually it's sort of activity which, just to give you some background, it started last year, and it started as initiative of habitat providers, like trying to set up sort of standards, because nowadays we are still, I mean, non-NASA's world, we are missing, for example, definition who is an analog astronaut, how much time you need to spend inside the habitat doing whatever activities to be considered as analog astronaut. So this is missing basically. And this was the reason why we started this initiative. It was created earlier this year. We went through some drafting, some comments from the world, and now we are just about to release the final version, which will serve as sort of guidelines and also like sort of maybe recommendation and some standards for analog space world, just to consider to first to keep crew safe as possible, but also to be realistic and to perform science at acceptable level, that it can be utilized also for future explorations.
So we do have a question that came in here from the audience. So do the analog programs develop a resource pool of SMEs, subject matter experts, that could be leveraged by industry for new developments? Anybody feel like they want to start with that one?
So I think we have a lot of, and it's distributed expertise, right? As you mentioned, it's a huge international community that's engaged in this analog work. It's not just NASA, it's not just ESA, it's everybody. There's a lot of distributed expertise. You know, there's not like a specific list of names that you just go and say, if I want to talk to the experts on underwater analogs, I go talk to X, Y, and Z. But the expertise is out there if you reach out to the agencies, to the analogs themselves. We're often very happy to share lessons learned, to share our expertise, to discuss ideas, that sort of thing. And I don't want to speak for the other agencies, but at least in my experience, that's kind of a pretty universal reaction to those sorts of questions.
So I would say that if you're going to reach out to someone who's participated in an analog to help you design equipment or whatever, you need to really understand what the analog was designed to do, so that you're matching the right twist of skill set with the goal that you're trying to accomplish with whatever design that you have. Because we've already talked about how each analog is trying to do a specific thing that's just a piece of the puzzle, right? So you need to really understand what those swim lanes are if you're trying to bring that information into designing the whole puzzle.
Now, I think I know the answer to this, but I do want to hear from you all. You know, there's no way to create this ultimate analog that's, you know, the perfect example of everything you're going to see in space. It's just no possible way. But is there a way that we can create a new type of analog that could test, you know, more realistic ways that astronauts are going to have to deal with Martian, like the journey to Mars or the Martian environment, or even, you know, the upcoming moon missions? Like, is there anything that we can do to even combine analogs or combine, you know, facility expectations and designs? Can we do anything like that to make as close as we can the ultimate analog experience? Or is it just not possible?
I think the key is what you said at first. It's not going to be one-to-one, right? I think we're always working to try to get closer to the missions, but it's really sort of pulling on what Sandy said. It's about understanding the mission and what you're really trying to do. So if you're trying to create an analog to answer both Mars and lunar questions at the same time, you're probably already in trouble because those are very different mission profiles. So you've really got to understand what's the mission profile you're trying to tackle, the questions around that, and go from there. But yeah, I mean, we're always developing new capabilities, adding on capabilities, modifying. You know, for the last half a decade, Hera, the analog at JSC, has been really focused on Mars types of missions and communication delays. Now we're shifting to more lunar operations and Artemis because that's a more immediate need. So it's definitely possible to shift, to add on, to add additional capabilities, to combine capabilities. We've seen multiple analogs add on, you know, boots on the ground EVA functionality if that's important to the mission profile they're looking at. It just depends on investment, right? Time and resource, because every capability you add costs money.
Right.
So I just want to comment that the communication delay bothers the ground more than it bothers the crew.
Absolutely. We've consistently seen that in the research we've done so far. Crews love the additional autonomy. The ground hates it.
Yeah. So I mean, you know, you think about operational scenarios in lunar and beyond. That's a dynamic that you need to think about, because trying to optimize communication delay might not be the right place to put the resources, as opposed to what is the proper dynamic that should be happening between the crew and the ground with respect to roles and responsibilities, and then back out from that, what's the kind of communication that we need to support that paradigm, right? So, I mean, you need kind of a bigger picture. You probably are thinking about that, but, you know, communication delay is not a problem.
Now, I know we're running out of time, but I do have one quick question also that, for my own curiosity, I don't know who's going to be best to answer this one either, so I'll keep it open. But how quickly are results that you obtain from analog studies actually incorporated into future missions?
I hate to say it depends, but I'm a scientist, so I say it depends all the time. It really depends on the specific question being asked, right? So SANS, I'll use as an example, it's a currently ongoing issue. So results from those studies looking at how to mitigate that issue are being turned around, discussed, and incorporated, or potentially incorporated, very quickly. Things that are focused on Mars, things that are focused on when we get to, I'll use the communication delay example, 20-minute communication delay. It's less urgent right now, right? Because we're not flying those missions yet. Now we're going to hit a point where, you know, in the technology development process, we've really got to get a grasp on it. But yeah, we are able to turn around those results and some of those mitigations pretty quickly, and incorporate those with the appropriate stakeholders for those missions. It just depends on kind of what the pull is at that time, if it's a more immediate issue or something that can kind of sit on the shelf for a little while.
I was going to say, and Sandy, did you feel like things that you brought back from the mission from NEMO as things that you were like, that's not really realistic? Did the crew on the ground listen to that when you were
Yeah.
back?
So when we come back from any mission, I mean, Nemo was one clearly, but even from my space missions, there's a very, very thorough debrief process where we go through and we talk to every community that had anything to do with the mission, from the training team to the engineering team to the ops team to the payload team to the photo TV team. I mean, any possible team that you can imagine. And we sit down and we give lessons learned. And then as a crew, we write a crew report that summarizes like our top 5 recommendations, if you will, lessons learned. And that goes into the black hole of wherever reports go. And those oral reports go into the black hole of wherever those reports go. And it's not clear from a crew viewpoint what happens with that information and how that information is incorporated into future. Now, it doesn't mean it's not, but it never was clear to me. I know there's a big database somewhere in the HRP program, and it's not clear how those lessons get extracted, but I can only hope that they are. I will tell you that my 16 years there, we would give feedback on certain things as a crew, and not my crew, but I mean a crew people constantly, and we would not see changes because you get into this, you get into the system, and then you've got requirements that don't get into the system for some reason because maybe it's too expensive or it's not higher priority, and it's like normal bureaucratic development engineering processes, but there is a way to get feedback, and then that feedback has to get processed. And I'm sure that happens with the analogs as well. Some of it filters through some of it, and there's a big database somewhere that someone can mine and go check this up from 1960 to today.
That's pretty accurate.
Yeah.
Well, I think that's a great way to end our panel today. So I wanted to thank each and every one of you for being here today and taking time out of your busy schedules to talk with me. And with that, I'll wrap it up. I think that's it. So thank you so much, everybody.
For a while, nobody was.
And may I?